Hello, please confirm that you can see the presentation.
Yes, sir.
Okay, thank you. Okay, so let us begin our discussion on this kind of a problem involving air resistance. So lately we have been discussing motion of objects through a fluid system, broadly fluid properties. So we have talked about the free fall of an object through a long liquid column. We have talked about the free fall of an object through air, long fall through air, and prior to that we talked about for object falling through a liquid column. Now we shall, so both of these two problems, fall through a liquid column, fall through air, talked about downward, were related to downward vertical motion. What we are taking up now is horizontal motion against air resistance. So bicycle motion against air resistance. So we began the discussion in the last class. So let me just quickly revise a few of those basic points we took up. Um, so this is a situation whereby you write first the force equation, which is standard Newtonian approach. Equation of motion, mass into the acceleration is the force. But this force is being imparted by the bicycle rider, and m is the mass of the bicycle and the rider together. But this force is not known, so we have to go about a roundabout way to try and set this up in terms of a few other things. So the kinetic energy of the bicycle plus the rider is half mv squared. So this kinetic energy comes from the work that is being done by the bicycle rider. I mean, energy is a conserved quantity. You can't create energy out of thin air. So this energy comes out as a result of the work being done by the bicycle rider. So we shall have to use that as our approach, in our approach, use that fact in our approach. So let us see. Now here, m dv dt is equal to the force. Now dE dt is the power. Energy, kinetic energy is equal to the work done. So basically, then if you can imagine this kinetic energy, or understand this kinetic energy to be the work, then dW dt is power, W being work done, power. dW dt is the power exerted by the bicycle rider. And that from this formula will be mv dv dt. Now, m dv dt is equal to, therefore, dE dt by v. So m dv dt is the force. So this is the force. Power output divided by the velocity. Now, for simplicity, we approximate this power output as a constant quantity, which is not a bad approximation. After an initial phase, when the bicycle rider slowly accelerates the motion, then the motion becomes steady. So, meaning that the bicycle rider is not pedaling, I mean, pedaling at a constant rate. Not, I mean, there's a limit to the rate at which a human being can pedal on a bicycle. So let's say that that maximum or optimum rate has been achieved, and the bicycle rider is pedaling at that constant rate. And therefore, the bicycle rider is doing work at a constant rate. And so the power that is resulting from that, power, always remember, is work done per time. I hope you have not forgotten that fact. This is, again, I'm referring to simple school knowledge of these concepts. So we approximate the power as a constant quantity. And so what we shall get is m dv dt is equal to f, so 1 by v, and dE dt is p. P is to be treated as a constant. So then we take the m to the other side, and from this equation we will get dv dt is equal to p by v by m. Okay, p is being treated as a constant. M, of course, is a constant. It's the mass of the bicycle rider plus the bicycle. So the only thing that is varying on the right-hand side in this formula is the velocity of the bicycle, I mean, the moving bicycle and the rider together, of course. So basically, this equation now is in an autonomous form, is an autonomous equation in the form dv dt is some function of v. A function of v is a very simple function, 1 upon v kind of a function, constant by v kind of a function. Now what we shall do is we shall rescale the variables. So p and m being constant, we take it to the left-hand side in the denominator, and what we do is that we put it inside the differential and define or rescale that small time t as capital T. Capital T will be small t into p by m. And so this equation is now reduced in a parameter-free form to look like dv d capital T is equal to 1 by v. All that I ask you to do now is simply apply your knowledge of what we discussed in the mathematical section just prior to that. In the last laboratory, I also gave you a mathematics problem sheet where you were given an autonomous function x dot is equal to fx. You just plot x dot versus x. Those were the kind of functions. You don't even have to integrate. I mean, ideally, you should be integrating this. Integration of this particular equation is not a very challenging task, but I wouldn't want you to do that immediately, because the whole idea is that you should, even without getting into too complicated mathematics, be able to extract information at a broad level before you start your computational work. So here we have that sort of a situation. This is like your x dot equal to fx, and you are plotting x dot versus x. So here x dot is served by dv, d capital T, and fx is, I mean, fv, that is now 1 upon v. So that is being plotted along the horizontal axis. So this is a rectangular hyperbola. I believe you are aware of what a rectangular hyperbola is. You know what a hyperbola is like. The equation of a hyperbola is x squared by a squared minus y squared by b squared is equal to 1, right? And incidentally, if it's an ellipse, then the minus will become plus. X squared by a squared plus y squared by b squared will be equal to 1 for an ellipse. For a hyperbola, it's the negative sign. We will discuss ellipse and hyperbola in more detail much later in this course when we talk about planetary motion. Remember, planets have elliptical paths. So we'll have the occasion to talk about all that. But in the case of a rectangular hyperbola, the asymptotes of the hyperbola are at 90 degrees to each other. And as such, the a and b have equal values. So the equation of an rectangular hyperbola is x squared minus y squared is equal to a squared. Whereas if it's a circle, it would have been x squared plus y squared is equal to a squared, right? So, but in the case of a rectangular hyperbola, it's minus y squared. So if you rotate the asymptotes of a rectangular hyperbola and make them coincide with the y and the x-axis, so the hyperbola would look like that. This is the hyperbola. The other branch of the hyperbola would be the third quadrant, which I have not drawn. So this is a rectangular hyperbola without air drag. And as you can see, when v goes to infinity, only then dv dt will go to 0. So there is no finite value of v at which this function will intersect this horizontal axis. Now, I hope you do remember from our discussion of these phase plots that if you plot x dot is equal to fx on the x dot versus x graph, if x dot is equal to 0 at a finite value of x, you call that point a fixed point. And then you analyze the stability of that fixed point either by a diagram or by a linear stability analysis. Now, if you look at this diagram, you can see that there is no fixed point in this diagram, meaning that at no finite value of v will this function intersect the horizontal axis. So when v goes to infinity, dv dt is equal to 0. So I have mentioned this statement over here, no fixed point for any finite value of v when there is no air drag. Remember, when you are riding a bicycle, you always also face a resistance, right? But here we have not a resistance due to air. Also, there is friction due to between the road and the bicycle tires. We have not accounted for that either. We will see what further complications can be introduced in this problem, or broader generalizations can be introduced in this problem by accounting for those factors. So here you have this sort of a thing. Now what we shall do is that we shall integrate this equation. We go back to our original equation, the non-rescaled equation, which was this. And so this equation is v dv dt is equal to p by m. So when we have that thing, we integrate that thing. The integral solution is found. V dv dt, dt is taken to the right-hand side, and p by m is a constant quantity, stays out of the integral. So the integral solution is found with an initial value of v is equal to v naught at t is equal to 0. So the initial value is slightly oversimplified, I would say. Of course, when t is equal to 0, velocity is not v naught, it's 0. Then you gradually start. But what we are doing here is that, let us say that after the bicycle rider has started pedaling, there is a certain phase where gradually speed is being built up. Right, and the bicycle rider is exerting changing power, not constant power. And so after a time when power has power expended or power generated, power output of the rider has become constant, then we set t is to be equal to 0. T is equal to 0. In that case, by then the bicycle rider has attained a speed of v naught. Right, so that is how you should understand it. So you put the initial condition at t equal to 0, v is equal to v naught, and then some general t you have here and v here. Integration is not a very challenging task over here. This is v squared by 2 with the two limits v and v naught, and this is pt by m between 0 and t. So the left-hand side will give you v squared minus v naught squared, and the right-hand side by 2, of course, and then the right-hand side will give you pt by m. And so you write this equation like this. And as you can see, this is when t goes to infinity, v squared will also go to infinity. So v is equal to square root of v naught squared plus 2 pt by m. So basically, when t goes to very large values, you can neglect this thing, v naught squared. And so basically, the behavior is approximately of the order of v is approximately of the order of t raised to half. Okay, I mean proportional to t raised to half or whatever you want to call it. So if you want to plot this diagram, starting with v naught, you will see that this function will grow, but this growth is at a decreasing rate. You just follow my point carefully. You see that I have plotted v versus t, and here v goes as t raised to half. Follow carefully. You put any general power of t, or you can just imagine it to be y versus x. Y going as x raised to alpha, right? If alpha is equal to 1, or let's say if v is just proportional to t, not t raised to half, you'll get a straight line. V is proportional to t, you'll get a straight line. V is proportional to t raised to a power greater than 1. Suppose t squared, then the function will go like concave upwards. So just remember, if you have a first power, you have a straight line. If you have a power that is greater than the first power, that is to say greater than 1, square, cube, whatever, you'll have a concave upward function. And if you have a power that is less than 1, as in half, it will go like concave downwards. That is like this. So grow to infinity at a decreasing rate. So that is what it is. So now, but the conclusion is that we can grow to any arbitrarily large value as t goes to infinity. So there is no limiting saturation value, right? But practically that really doesn't happen. We will see how we can now introduce some generalizations. But before that, if I were to ask you to integrate this thing, see, this is the integral solution which you have been able to compute or calculate. Calculate by hand by simple school level integral calculus. This is the answer. But if I were to ask you to integrate this function numerically or computationally, what will you do? Just by applying Euler's method, dv dt is equal to p by mv. So by Euler's method, you will have to apply the standard prescription, vi plus 1 minus vi by delta t is equal to p by m vi. So ith step you will get, let's say you start with delta t is given as some time step. It is up to your judgment as to what delta t can be. You can immediately see that here's the time scale for t. The time scale of t is m by p, right? Time scale of t is m by p. So whatever time scale you want to put, you put, and then you integrate this equation by your computer code, Euler's method. Mostly, as I have been saying, Although I have asked you to work on Taylor's second order, third order, all these things, if you can do Euler's method by taking a suitable time step, I think you would have done a good deal. Thereafter, Taylor will only add some extra refinements, but the basic principle is always contained in the Euler method and the choice of your time step. So if you can understand that, you have done most of the thing. So that's why most of your, I mean, right now, I'm asking you to do things by second order Taylor method, third order Taylor method, all these things. But the fact is that second and third order Taylor methods are also quite complicated, can also be complicated if the function becomes complicated. In that case, you're simply required to do stuff by Euler's method. So that's why you understand Euler's method very well. Here's the algorithm of that. Okay, anyway. So now we will make some broader generalizations in this problem. What happens if there is air resistance? So far, we have not considered that. So far, air resistance has not been considered. Air resistance will offer a drag force. You have to work against air, right? As you bicycle through, let's say, for your morning exercise, if you're bicycling on the, bicycling track or wherever, you will experience air resistance. The faster you go, greater you will feel the resistance to be. It's a matter of common knowledge, right? If you are even if you're a common bicycle rider, not a bicycle racer or anything more complicated like that. So let us see. We will start with a little broad discussion. The air resistance offers a drag force. We are writing the drag force capital D to be proportional to both the first power of the velocity and the square power of the velocity. The negative sign implies drag, which means resisting motion, and B1 and B2 are proportional constants. Now, you noticed I've written V and V squared. Now, you will say, why have you kept both? Let us see. That's a generalization. If you were falling through a liquid, if you were traveling through a liquid, your drag force will be proportional to V, with a minus sign, of course. Here, drag force is proportional to V with a minus sign. If you are falling through air, your drag force will be proportional to V squared. This little discussion gives you that idea. There is no precise mathematical prescription for this. This is just an experimentally understood, observed something. Liquid, first power, air, second power. We have, in this case, kept both, right? The two terms on the right-hand side. Now let us have a little mathematical discussion of this thing. So this is the general drag force, as if this part would come from liquid, this part would come from air. We have retained both. And now the two terms on the right-hand side of D resemble a Taylor expansion in V. I hope you know, if I were to ask you to carry out a Taylor expansion about a certain point of a function V, then there will be a zero order term, then there will be a first order term. Incidentally, the first order term will be like this here, and then there will be a second order term, and etc. like that, a cubic order, whatever. So you have done all these things, Taylor order or expansion of autonomous functions. You can do that. So here we have that sort of a thing. Now, usually what happens is that when you have high velocities, the V squared term is more dominant compared to the first order term. Remember this one thing, small values of a variable, the lower powers are more important. Large values of a variable, the higher powers are more important. Take a number half, which is less than 1. 1 is the scale in this discussion. Take a number half. You square that, half will become 1/4. So the higher power is smaller than the lower power for a number less than 1. Take a number 2. Square that, higher power is 4, which is greater than the number that you started with. The scale here is 1. So small number, lower powers dominate. Large numbers, higher powers dominate. So here we keep only the V squared term. Now, what is the justification for us to, I mean, that's just a kind of a fond mathematical hope that when you have high velocities or high values of a variable, we retain the higher power and ignore the smaller power just for simplicity of calculation, right? How is it justified from a physical perspective that we are dropping the first power and we are only keeping the second power? Let us discuss that first. Let's not worry about bicycle or anything. Let's worry about, here's a little diagram uh, for you to understand what I have asked you to move. Let's say long, a broad, a wide and broad rectangular object. Let's say a tabletop, right? A tabletop. I'm asking you to move the furniture from one room to another. So this is the tabletop. You're holding the tabletop with on both sides with your hand, and the tabletop is being held vertically, and you are moving forward. So this is like an object with a frontal surface area, capital A. This is your tabletop, moving forward through a distance dl. So you have moved with the tabletop. The tabletop is not flat and horizontal now, it's vertical with like a wall. You're just moving it from one room to another. I've asked you to move the furniture. Okay. So you're holding the tabletop and then you're pushing it forward. And this is just a simple discussion. I mean, it's not got nothing to do with bicycle or anything. It's a general discussion. It could have been this frontal surface area could have been of any other shape, circular table, whatever you want. I'm just giving a simple idea here. So you have moved this frontal surface area through a length dl, as has been written over here. So this has moved with the velocity v. So through time dt, through a distance dl in time dt. In time dt, at the start of the time dt, the front was here. At the end of the time dt, little time window dt, the front has come here. Okay, so it has moved through physical distance like this. Okay, now in so doing, I mean, there was air in this whole area. So this frontal surface area, your tabletop or whatever, in order to move it, you have had to push the air contained in this box out of the way. So the mass of the air displaced, pushed out of the way by the frontal surface area and moving a distance dl. So how much air has been moved out in this small time dt, having traveled through a distance dl? A little bit of the air that was being occupied in this box had to be moved out, pushed out of the way for this surface to move from here to here. So how much air has been moved out? Roughly that will be density of air contained in this box multiplied by the volume of that box. So density of air is rho, and the volume of this box is A dl. So that is the amount of mass of air displaced, in which rho is the density of air. So, okay, so that is the mass of air displaced. Now the frontal surface area travels with a velocity v, and what is v? V is dl dt, as has been written over here. Okay, now the air that has been moved out also picks up that much, approximately picks up approximately that much velocity. How so? I mean, this thing has come with the velocity v and pushed the air out of the way. Just imagine you're standing, your friend comes running from one side with a certain speed v and pushes you. Now you'll of course be thrown forward, meaning that you would have acquired some velocity. Now that velocity will be of the order of, I'm not saying exactly equal to, will be of the order of the velocity with which your friend has pushed you, right? So if your friend has come at a very fast speed and pushed you, you'll be thrown violently forward. If your friend has come slowly and has just given you a small prod, you'll just, be a little disturbed about your shift a little about your initial position earlier, whatever you were. So the kind of velocity you acquire on receiving a force will be of the order of the velocity with which the force, the object that has imparted the force, travels. So basically, it's the same thing. The air was still in this box region, and suddenly this object with the frontal surface A has come from the left-hand side and given it a push. The air has moved out of the way, and in so doing, it has got some velocity that is roughly of the order of the velocity of the moving object. So the displaced air with a mass rho a dl acquires a velocity of the same order. Fine. So now you can find what is the kinetic energy of the displaced air. Approximately, this is not exactly equal to the kinetic energy of the displaced air, E subscript kin, Kin, is mass into half mv squared. Half mv squared is written like this. Rho a dl is the mass, v squared by 2. Now, where has this energy come from? So the energies has come from, in this case, we are talking about a general object, but in the case of the bicycle rider is also riding forward. The bicycle has got a front, although it's a very thin front, and the bicycle rider has also got a front. So there is some air in front of the bicycle rider system that is being pushed out. So in this case, the displaced air um, is being pushed out with a kinetic energy that is being provided, that is coming from the work done by the bicyclist, right? So the cyclist is providing this energy. This energy can't, once again, come out of nothing. It has to come from something. So the bicycle rider is doing work. With that work, the bicycle and the rider system is moving forward. And in so moving forward, it is displacing air out of its way. And this displaced air, in being pushed out, is acquiring some speed. And in acquiring some speed, which is the speed is of the same order as that of the bicycle plus the rider system. And the kinetic energy is this. So the work is being done against the air drag, right? So the air doesn't want to move out. So the bicycle rider has to push forward through this air medium. And so the air will offer some resistance. So the work that is being done is that it will be minus dl. Why minus? Because d is the drag force. So the negative signs, the work done, is minus d, capital D into dl, the negative sign indicating that the drag force applied is opposite to the drag, the force that the bicycle rider is applying is opposite to the drag. So the drag force is resisting motion. So to overcome the drag, you'll have to apply at the very least a force that is equal to the drag with a minus sign, meaning opposite to the drag, and then work done is force into the displacement. So minus capital D into dl. So that is what you have. Minus capital D dl is the work done, and that work done being done is translated as the kinetic energy of the air displaced. So you just make an approximate balance of the two quantities over here. So minus d capital D into dl is equal to rho a small dl v squared. So the two dl's will cancel from both sides, and the drag force is approximately equal to minus half rho a v squared. More generally, we have made several approximations over here, so that's why we shouldn't put too much faith on this number half here. More generally, we call it b as constant, right? In which b is equal to half is a drag coefficient, is of the order of nearly approximately equal to half. It can be slightly different from that, but something of the order of that it will be. Now, if you look at it, this capital D is equal to minus an experimental a constant that is to be determined experimentally times the density of air times the frontal surface area times the square of the velocity. And that corresponds to, let me first read out this statement, in which B is approximately equal to half is the drag coefficient. It can have a slightly varying value. The drag force can be reduced by reducing the frontal surface area, right? Bicyclist crouching. It is also reduced for lower air density. I'll just, first thing that I'll do is that I'll go back to the old formula that I began with. Capital D, the drag force is minus first power proportional to minus first power V minus second power V. Now we said that we neglect the first order term. This can be general. We neglect the first order term and we keep only the V squared term. What is the physical justification for this thing? I mean, the mathematical justification is that since V squared is supposed to be high, why high? Because we are traveling through air, not through water. I mean, bicycling through water is far more difficult than bicycling through air. Anybody who has had to bicycle through a waterlogged street in a city like, let's say, Mumbai, in the monsoons, there is always constant waterlogging. You would know what I'm talking about. So bicycling through water is far more difficult than bicycling through air. So usually if you're bicycling through air, then you will attain higher velocities. So you will say we'll keep the V squared term and neglect the first power term. That's a mathematical justification. Where's the physical justification? Here is the physical justification that I have just discussed. That this whole business of pushing an object through air and the resistance that it faces, displacing air out of the way, all of these things will show that the drag force that one experiences is indeed proportional to the square of the velocity. You see that? This is minus some constant into v squared, just like this thing. That's first point. Second point is that larger the frontal surface area of this object, larger the frontal surface area, greater will be the drag resistance. That's a matter of common experience. That is why, to reduce, in the case of the bicyclist, to reduce the frontal surface area and have a smoother passage through air, a bicyclist would reduce the frontal surface area presented to the air. What, by doing what? By crouching on the bicycle. You don't just sit straight up on the bicycle. You crouch over the bicycle, create some kind of a streamline, wearing a helmet and all that. Your body is almost horizontal to the ground, not perpendicular to the ground. If it's perpendicular, then you'd be presenting your chest and your front part of your body against air drag. So you crouch down, make your body horizontal to the ground. So you're just effectively presenting your head, the top part of your head and your shoulders, and not much more area than that. So that's the whole idea. You're reducing the air. And it is also reduced a lower air density. That's understandable. Greater is the density of the material through which you have to bicycle through, greater will be the resistance. Just a while ago, I gave you a naive example, like try bicycling through water. You'll immediately realize that it's not a very easy task to do. Okay, by the way, lower air density is not always a very good thing. All right. For instance, lately these days in America, a slight problem has started happening with aviation companies, aeroplanes. What has happened is that because of global warming, suddenly it has become it becomes very hot in the summer months. I mean, unusually hot in the last few years. It's been so. In America, people travel more by plane than by train. Here in India, mostly people travel by train. It's only a small percentage of the population that fly by plane. But in America, almost everybody. So plane aviation is a very important public transport medium there. Now, what happens is that because of the summer, the air becomes very hot over runways, and hot air becomes thinner, rises and becomes thinner. As a result, planes require to taxi much longer on runways to get the airlift. That is the problem. So now they need longer runways because of this hot air over runways. So as I said, I mean, we will discuss certain aspects of these things later. So this lifting of planes and all that by Bernoulli's equation. But I'm just giving you, so lower air density is not always a good thing if you want to achieve faster speed, by the way. But that's plane technology is different from bicycle technology. So the discussion is a little stretched. Okay, anyway. So now let us go back to our original equation. Our original force balance equation was m dv dt is equal to p by v. Put the m to the left hand side and you'll have m dv dt is equal to p by m. Sorry, p by v, I'm sorry. M dv dt is equal to p by v when you are not accounting for air drag. When you are not accounting for air drag, m dv dt is equal to p by v. But once you have accounted for air drag, this will be the equation. Without air drag, this thing is zero. And so you just have m dv dt is equal to p by v. But now this thing has to be accounted for. So it is minus b rho a v squared as we got from this drag formula. So equation for a bicycle motion will have to be modified by this thing. Again, as you can see, this is an autonomous equation. I'm taking the m to the right-hand side, and so dv dt will be equal to p by mv. That's equal to minus m rho av squared by m. Okay, what I will do now is that I will do a little modification of this equation. Basically, I'll be multiplying this whole equation. I want to have this v squared, this term, without any coefficient. So what I will do is that I will multiply this equation throughout by mv by b rho a. So this is an autonomous equation in the form dv dt is some function of v, but now I'm doing something else. mv by b rho a, that is the factor by which I multiply this thing. So mv by b rho a dv dt is equal to p by b rho a. The mv and the mv will cancel, minus mv multiplied by v will give you v cubed over here by b rho a. All of these things will cancel and you have this quantity. Okay. Now you can see that the right-hand side has got a cubic order dimension of velocity. Dimensionally, this is cubic order. So this must also be, dimensionally speaking, of the cubic order. You can check that thing, power by density by area. So ultimately, it will come out to be L cubed by T cubed dimensionally. You can check it out for yourselves if that's not a big challenge. So I will define this thing as a new constant A cubed, where A and V have the same dimension. So this thing will be defined as A cubed. Okay. And so defining this thing as A cubed, now let us see what we have got over here, m by b rho a into v dv dt. Okay, so what we are doing is that now we are defining a new quantity, u is equal to v by a. With this definition, we are dividing this equation throughout by a cubed. So dividing throughout by a cubed, this will be a cubed by a cubed will be 1, v by a will be u, so 1 minus u cubed on the right hand side. Now I will divide the left hand side by a cubed. So there are three a's over here, a into a into a. One a will reduce this v by a to u. Another a will reduce this v by a to another u. And the third a will remain outside. M by a b rho a is a constant. Now what I will do is that I will absorb this a b rho capital with small a capital A by m as a constant within this time differential d small t. And so it will be AB rho capital A into small t by m. Putting this together, I will call this thing as d capital, I'll call this thing as capital T. Okay, so now you can see your equation is now nicely reduced to an autonomous form, u du dt into 1 minus u cubed. I'm dividing this equation throughout by u, so you will get du dt is equal to 1 minus u cubed by u. This is u. And so it will be 1 by u minus u squared. So it's an autonomous form, du dt is equal to fu. Okay. Now how will you find the fixed points of this autonomous equation? Simple strategy. Du dt is equal to 0, just like x dot is equal to fx. How will you find the fixed points? Very simple algebraic work. X dot is equal to 0. So basically fx is equal to 0. So now you have this thing. So du dt is equal to 0. So what I will do is that I look at this equation, 1 minus u cubed by u. This is the by u part. 1 minus u cubed by factorizing is written as 1 minus u into 1 plus u squared. Okay, so this whole chunk will be equal to 0. So under what circumstances will you have du dt going to 0? Let us see. Either u will have to go to infinity. In the denominator, u becomes infinitely large, and so this will become 0. Or u is equal to 1, in which case this factor is 0, or 1 plus u squared will be equal to 0. Now, of all these three scenarios, which one is the physically most feasible? A fixed point has to be found, can only be found for a finite value of u or x. If I say find the fixed point of x dot equal to fx, you can't find a fixed point if fx doesn't have a 0 for a finite value of x. Like in this case, there is no 0 of dv dt for any finite value of v. So no fixed point for any finite value of v with no air drag. So there is no fixed point here. So similarly, here also, let us see, you will have a 0 of this thing, but only when u goes to infinity. But that is not a fixed point. Fixed point has to have been at a finite value. U is equal to 1. Certainly, this is a fixed point. What about this part? 1 plus u squared is equal to 0. You can solve this equation. I leave that to you as an exercise. Solve this equation. This is a quadratic equation. I hope you know what the formula of a quadratic solution is like. Minus b plus minus b squared minus 4ac, whole thing divided by 2a, right? A and b are all equal to a, b, c are all equal to 1. So b squared minus 4ac. So b squared will be 1 minus 4ac, b squared 1 minus 4. So that is minus 3 square rooted over. Minus 3 square rooted over will give you a complex. Both roots will be complex. So this is not a physical scenario. U going to infinity, 1 plus u squared, 1 plus u squared is equal to 0 will not give any physical meaningful roots. So you will just have u is equal to 1 as the a physical fixed point. So u is equal to 1 meaning v is equal to a. V is equal to a meaning, I've just made a slight mistake over here. A cubed is equal to P by B rho A. So V is equal to A meaning this whole thing raised to 1/3 power. I wrote, forgot to wrote that, I mean, by mistake, I did not write that 1/3 power. But in your table of corrections, that correction has been made. Remember in page 16, page 15, there's a correction to be made at the bottom formula. Anyway, let's not worry about that now. Let's see how we will plot the function. Du dt is being plotted along the vertical axis, u is being plotted along the horizontal axis. So at u is equal to 1, you have a fixed point. Above, between the origin, you start with an initial value of u naught, like you started with an initial value of v naught here, not starting at v is equal to 0. You started at an initial value of v naught here, and then you proceeded. And so it is that you start with an initial value of u naught here. Now this function is above the horizontal line, therefore a rightward turning arrow is to be assigned. Then at u is equal to 1, this function intersects the horizontal line. And then it falls below the horizontal line, and there's a leftward arrow over here, which means that this is a stable attractor. So you have to blacken it with the arrows pointing towards it. So u is equal to 1 is a stable attractor. Now, what guarantees that I have drawn the plot correctly? Qualitatively, I have to be sure that I've drawn the correct plot. How is it that it is going down like this? And then after that, it is curving down like this. Why not going up like this or any such thing? Let us discuss that. That, of course, at u equal to 1, there will be an intersection. When u is very much less than 1, let us look at the function here. When u is very much less than 1, 1 by u will be, u is a very small number now, since it's very much less than 1. U squared will be a very small number, even smaller number. But 1 upon u will be a very large number. 1 upon u will become very large. Therefore, when u is very much less than 1, 1 upon u will become very much greater than u squared. So du dt is approximately equal to 1 upon u. What about the other side? When u is very much greater than 1, when u is very much greater than 1, 1 upon u will be very small compared to minus u squared. U squared will become even greater. So when u is very much greater than 1, du dt will be approximately equal to minus u squared, because 1 upon u will be very much less than u squared. At u equal to 1, both terms balance out and du dt equal to 0 to give a fixed point at u equal to 1. Around u equal to 1, that is, give a fixed point. So for values of u much smaller than 1, the behavior is approximately like a rectangular hyperbola. Hence, I have drawn this thing. For values of u very much greater than 1, the behavior is with a downward curving parabola. You see, the behavior will become du dt will be equal to minus u squared. You can just plot y is equal to minus x squared, and you'll see a parabola curving down like this, right? So here's the answer. So the phase plot has the form of a rectangular hyperbola when u is very much less than 1, and for u very much greater than 1, the phase plot has the form of a parabola. And since the stable fixed point at u is equal to 1 is approached for t going to infinity, you will say, why should t go to infinity? And why? And where have I seen this thing from? Well, in order to understand that, I will just stop the sharing here for a minute, and I'll go back to your math note, right? In your math theory, we discussed the phase plot of, just give me a minute. Sorry, just a minute. Here, please just confirm that you can see this presentation, the math part. Hello? Can you please confirm?
Yes, sir.
Okay, thank you. So you see, this is a fixed point. Just a simple equation, x dot equal to a minus bx. This is a phase diagram. This is a fixed point. Sorry, just a minute. Yeah, just a minute, please. Yes, so now this fixed point is a by b. X dot versus x diagram shows it to have a finite position on the x-axis. But if you plot it along in the x versus t diagram, you will need infinite amount of time to reach a by b. In time, in real time, you will need infinite amount of time to reach a by b. You have checked that thing in all these things. So similarly, for the logistic equation, you'll need infinite amount of time to reach this limiting value. Now, why will you need infinite amount of time to reach the limiting value? The answer is given here, stability of fixed point. If you start at a slightly deviated distance away from the fixed point, epsilon is the slight deviation, howsoever small it be, but if it's slightly deviated away from the fixed point, to reach the fixed point, you will need infinite amount of time. You can see that this is very close to the fixed point. That is why we carry out a linearizing argument. If it had been farther away from the fixed point, then epsilon would not have been a small number, but this principle would have held. In that case, if epsilon had not been a small number, you could not have ignored the higher powers. That is fine. But whatever it is, to make epsilon go to 0, that is to say, to make x go to xc, you will need the passage of an infinite amount of time if the fixed point is a stable fixed point. So in all of these problems, the fixed point, I mean, in some of, not, I'm sorry, in some of these problems, this is a stable fixed point. So from here to here, if you have to go, follow this point carefully. X naught to x equal to a by b, if you have to go, it's looking like a finite distance here, but it'll take infinite passage of time. To start from here to here, if you have to go, you'll need infinite time. Similarly, if you have to go from x naught to a by b for the logistic equation, x naught to a by b, you will need infinite time to reach this point, right? So you will need infinite amount of time. It doesn't matter how far you are from the fixed point. If the fixed point is a stable fixed point, you will eventually reach that fixed point. That is all right. But doesn't matter how far you are away from that fixed point, small distance, large distance, whatever, you will still need infinite amount of time to reach the fixed point. That is the understanding you should carry forward in all of these fixed point problems. I'll go back to my old bicycle notes now. So I'll stop the sharing. So be clear on this particular point. Okay, so let me resume the discussion. Here. Okay, so I believe you can see this thing. At least I can see that it's being shared with you. Okay, if you can't see it, you can let me know immediately. Anyway, so as I said, there's a correction to be made. P by B by rho A raised to 1/3. V is that. And so that correction has to be made over here. Since the stable fixed point at u is equal to 1 is approached for t going to infinity, there is a finite limit to the velocity. V is equal to P by B by rho A whole thing raised to 1/3. V is equal to P by B rho A whole thing raised to 1/3. As I said, at the bottom of page 15, there's a 1/3 power to be put above this. Here in page 16, there's a 1/3 power to be put here and a 1/3 power to be put here. So this is V is equal to P by B rho A raised to 1/3, or U is equal to 1. Growth converges to a finite limit for t going to infinity. This is quite different from what you saw here. When you did not account for air resistance, you would have thought that you'll grow to infinitely large value of V. But in reality, that doesn't happen. You will grow to only a limiting value, and that limiting value, that appreciation could be had from this graph here. And so this will, how it will happen. It will converge to a finite limit for t going to infinity. Now here's a little discussion, extra discussion, but this is not a very necessary discussion. Why am I, this discussion is just to demonstrate to you that as soon as you get an equation, don't start integrating straight away, right? Before you start integrating with the equation, you can just do some simple tricks on it, apply some simple tricks on it and extract as much information as it is possible, right? So don't get into any complicated treatment. Like, in the medical profession, a doctor is considered very good if the doctor cures a patient without getting into too much complicated hospitalization or surgery or anything, although the patient may be having a very serious ailment. But if a good doctor can diagnose the symptoms properly and recommend simple um, medication techniques, a simple treatment, then that doctor is considered good. Integrating an equation like this is pretty complicated. And at the end, it will not help you much. You will not see. So far, what have we done? We have just taken this equation, we have carried out a fixed point analysis by plotting, by carrying out a phase diagram, and we have got all the necessary information. I mean, earlier, without this drag force, we knew that there was no fixed point in this system. It will go to infinite value of velocity. Doing this integration, doing this phase plot analysis, these were not difficult tasks. Now we have got a slightly more complicated equation on the application of the drag force, right, or the introduction of the drag force. Now, we've still carried out the phase plot analysis by hand. You can do it by computer, but suppose you don't have the advantage of a computer. You're living in a very remote place. There's no power or any such thing. What will you do? You still have pen, paper. And incidentally, for centuries, for thousands of years, human beings have been doing that thing only. Computer is not just a century-old business, not even a proper full century, right? So you have actually extracted up to this point, you've actually extracted all the meaningful conclusions. Integrating this equation will not give you anything new. Let us see how. I have got this equation over here. Du dt is equal to 1 minus u, 1 plus u squared by u, right? I will say, let's now look at the integral solution and try to find out u as a function of t, and then reconvert them back to our old variables and plot u versus v versus t. Do we get anything meaningful out of that? Let us see. This discussion is meant to show you that one has to be a little judicious and clever. So let us see. This integral is this thing, sorry, here. U du by 1 minus u cubed is equal to dt. This integral, u by 1 minus u cubed is du is equal to dt. So this is the integral. U du 1 minus u cubed is equal to dt. Then I put integral signs. You can see it's a very complicated integration. I mean, we keep going on and on and on for a long time. Let's see now. I'll have to, and then at the end, you'll not come to much conclusion. So that's why this is meant to demonstrate to you that don't start integrating straight away. Use simple tricks first to cure or solve the problem. You're a doctor and you don't want to trouble your patient too much by getting into complicated treatment procedure or hospitalization. Here's this thing. U divided by, you factorize this thing, 1 minus u into 1 plus u squared. Okay, partial fractions. U divided by 1 minus u, the first part, and then this is the quadratic part, so you will write the numerator as a first order function, bu plus c, 1 plus u squared. Recall your school knowledge of partial fractions. I believe your memory about all that is intact still. Okay, then you multiply this whole thing by 1 plus u squared into 1 minus u, and this is the equation that you get. So now there are three unknown quantities, a, b, and c. Okay, so when u is equal to 1, this will be equal to 1. A into 1 plus 1 plus 1 will be 3. And 1 minus u will be 0. So basically, a into 3 is equal to 1. Therefore, a is equal to 1/3. When u is equal to 0, this will be 0. This will be a into 1 plus 0 into 0. So a into 1 plus this will be 0. And this will also vanish. So you'll just be left with c, a plus c. Therefore, c will be equal to minus a. And hence, it will be minus 1 by 3. When u is equal to minus 1, u is equal to minus 1. If you have u is equal to minus 1, let's see now. Minus 1 on this side, then you have got a into 1 minus 1 is 0, plus u squared minus 1 squared will be 1. So a is equal to u is equal to minus 1. So minus b plus c, 1 minus of minus 1 will be 2. That is what you have. So then you solve for this equation. A is equal to minus 1/3. So you put all these things together and you'll be able to see b is equal to 1/3. Okay. So now a is 1 by 3. Sorry, a and yes, a is equal to 1 by 3, b is equal to 1 by 3, and c is equal to minus 1 by 3. A is equal to 1 by 3, b is equal to 1 by 3, and c is equal to minus 1 by 3. If you have split this integral into two partial fractions, this is what your integral will be like. Minus, 1 by 3 du by 1 minus u. This is a, and this is b minus bu minus c. Bu plus c, but v is 1/3 and c is minus 1/3. So the minus stays over here and 1/3 comes out. Okay, so this is it, and the last term is dt. Okay, so this is the ut integral. Let's see now what we can do. This is just school level integral calculus. Variable substitution and all that. So there is minus u over here and there's u over here. So I want to do the integration over the variable minus u. So what do? I put a minus u here and a minus sign outside. So minus 1/3 d over this variable minus u. So the integral will be log of 1 minus u. Fine. Second part, 1 by 6. You notice that you've got a u plus minus 1. So what I'm doing is that, and there's a 3 over here. So first I'm multiplying this numerator by 2. So I will get 2u minus 2. And then in the denominator, I'll get 2 into 3, 6. 2u minus 2, and then the minus 2 I'm writing as plus 1 minus 3. Okay. So plus 1 minus 3, after having written that thing, if you look at this thing, 2u plus 1 is the derivative of the denominator u squared plus u plus 1. So basically, this part, 2u plus 1 divided by u squared plus u plus 1, could be integrated as 1 by 6 log u squared plus u plus 1. And then you have got a minus 3 by 6, which is half of du u squared plus u plus 1 is equal to capital T. We are still not done. As you can see already, I mean, the integral has become pretty complicated. Our task is to write u as a function of t in closed form. Well, we shall see. It can't be done. Anyway, now we shall have to tackle this part, u squared plus u plus 1. What do we do with this thing? It's a quadratic form. So u squared plus u plus 1, we are writing as u squared plus 2 into half u plus 1. Then this part, we are writing as u squared plus 2 into u plus half plus 1/4 plus 3/4. One I'm rewriting as 1/4 plus 3/4. And that 1/4 part is being put with this thing, and we are writing it as u plus half whole squared plus 3 by 4. If you break it open, you will see it will be u squared plus 2 into half into u plus 1 upon 4. 2 into half into u is this, and 1 upon 4 plus 3 by 4 will give you this 1. So there you are. So basically then your integral is minus half du u squared plus u plus 1. This thing is written as 3 by 4 plus u plus half whole squared minus half. Then I'm taking this 3 by 4 out of this integral. So 3 by 4 in the denominator will give this thing as 4 by 3. 4 by 3 into du plus 1 plus this whole thing. So when how have I written this thing? Whatever is left outside will be 4 by 3 into u plus half whole squared. This thing to the right of this vertical line. 4 by 3 into u plus half whole squared. Then you take the 3 inside the square order and 4 also inside. So it will be 2u plus 1 by 2 into 2, which will make it 1, and the 3 goes in the denominator, 2 root 3 and root 3 whole squared. So this whole thing will be this thing. Next task. As you can see, there's no end to this thing. What you will do now is you will define tan theta. This thing is 1 plus something squared, right? And so we are looking at this formula, sec squared theta is equal to 1 plus tan squared theta. Sec squared theta is equal to 1 plus tan squared theta. So 1 plus this whole thing squared, we will write that thing as tan squared theta. So tan theta will be equal to 2u plus 1 by root 3. Okay. So now we will have to substitute the u in terms of theta. So when you take the differential of this thing, it will be sec squared theta d theta plus 2 by root 3 du. Okay, so we have to now substitute the du here as root 3 by 2 sec squared theta d theta, root 3 by 2 sec squared theta d theta. And so our integral will be minus half 4 by root 3, this thing in the numerator, integral du by 1 plus 2u plus 1 root 3 whole squared is minus half 4 by root 3. Du is root 3 by 2 coming out, sec squared theta d theta, this thing, and this thing is 1 plus tan squared theta. 1 plus tan squared theta is also sec squared theta, so this sec squared theta and this sec squared theta is cancelling, and you'll just have integral d theta minus, so there's a whole lot of cancellations here, 4, 2, 2, root 3 and 3, so minus 1 by root 3, and then you have d theta, and so the integral will be theta, and so when you have the theta, you go back, so what will be, if tan theta is equal to this thing, theta will be equal to minus 1 by root 3, tan inverse, or arctan 2u plus 1 by square root of 3. So now, after all your hard work, here you are. The full integral solution is not in closed form, minus 1/3 log of 1 minus u plus 1 by 6 log of u squared plus u plus 1 minus 1 by root 3 arctan 2u plus 1 by root 3 is equal to t plus constant. The only conclusion that you can draw from this thing is that when t goes to infinity, look at this equation, when t goes to infinity, the only conclusion that you can possibly draw is that you will have to go to 1. Otherwise, there's nothing else that you can do with this equation. You'll say, why should you go to 1? Just look at this thing. When u goes to 1, you will have 1 minus of 1 will be 0. Log of 0 is minus infinity. Minus infinity with a minus sign outside will again be infinity. So t going to 0, log minus 1 by 3, log of 1 minus u will go to infinity. About the other things, you can't conclude anything. Why have I gone through this whole trouble of integrating an equation which really does not give any more insight than what we have got by doing this simple analysis? Once again, I caution you that there should be a 1/3 power here and a 1/3 power here. Why have I gone into so much trouble? Just to demonstrate to you that don't straight away start integrating. You will not always get a very simple integral to work with. Here, we had a complicated integral. Nevertheless, we were able to do the integration. Sometimes we may not even be able to do that. And even after doing the integration, we are not able to write this thing in a closed form. What do I mean by not in a closed form? A closed form integral will be u is a function of t. We can't do that. I mean, you can't open all of these things up and then say, I mean, just see, trying to solve, write u as a function of t, you can put the two logs over here, but what about the arctan part? You can still do this thing as a log of u squared plus u plus 1 divided by divided by 1 minus u. All the 6 and 3, all those business will be there. Fine, that's all right, but the arctan part. So when I say write an integral solution in closed form, this is an integral solution in closed form. V as a function of t. Without air drag, you're still able to do that. With air drag, accounting for air drag, you'll not be able to get v as a function of t. First, you'll have to get u as a function of t, and then you'll have to go back to your old variables following these definition, and you should be able to write v as a function of t. If you can write u as a function of capital T, but you can't. So basically, this entire integral process doesn't give you any more information than what you have been able to achieve by this simple phase plot analysis, right? Cautionary tale here is that occasionally you may not be able to get an analytical solution. Even if you get an analytical solution, it may not be in a closed form. Therefore, all this bag of tricks, applying phase plot method, doing a little plot over here, doing a little approximation there, all these things, a little approximation to show that this is a rectangular hyperbola, this is an inverse parabola, all of these things will help you in your numerical work, or at least to judge that your numerical work is authentic. Anyway, one last point on this bicycle rider problem is that if you have to do this thing numerically by Euler's method, what is it? dv dt, delta v by delta t, which is dv dt is equal to p by mv minus b rho a by m vi squared. Is that so? Yes. And then this is the Euler prescription. Vi plus 1 is equal to Vi plus P by M Vi dt delta t minus B rho A by M Vi squared delta t up to the first order. This equation that we are getting here comes from here. And this equation that we have comes from here. dv dt is delta v by delta t is equal to p by mv minus b rho a v squared by m. This equation that you have, when broken up in Euler's formula, gives you this. So up to the first order. So as you can see, the bicycle rider problem is simple from one perspective and not so simple from another perspective. If you are carrying out, working on a problem like this, you have to be judicious. You have to apply your judgment. It's a matter of experience. There is no handbook that tells you how you should apply your judgment. That is why some people are good in making a judgment and some other people are not. Right? For instance, I'll just give you a simple cricketing analogy. MS Dhoni was considered a very good captain. Why was he considered a very good captain? At a moment's notice, he would be able to sense an opening in the game and exploit it quickly. Other captains may not be able to do it, right? So that's the whole point. If you are a good doctor, you look at a patient without getting into too much complications, you will recommend a course of treatment that will cure the patient. Or if you are just going by the handbook and anything, you can do a whole lot of surgery and all that, and at the end you will not get too much benefit for all the expense and the trouble that you will undergo. So here it is like this. This is too complicated a treatment, doing all the integral. Of course, you have to find an integral solution. That's a textbook prescription. But is the integral solution giving you anything useful? Why go into the trouble? So that's something that you'll have to apply your judgment. So that's why keep all of these bag of tricks handy whenever you're given problems like this to work upon. So we have finished three kinds of problems of motion through fluid medium. First is vertical downward motion of an object through a liquid column. Second is vertical downward motion of an object through air, which is not a liquid, but both are fluids. Liquid is incompressible fluid, air is compressible fluid. Third kind of problem that we took up was horizontal motion through air, right? Horizontal motion through air, that is, in this case, bicycle motion against air resistance. Of course, you can very well say that why have we not accounted for the friction of the ground on the bicycle tire? You can account for that. I'm not saying that you should not, but then usually what happens is that on these bicycle tracks, the roads are designed in such a way that there is, I mean, a little bit of friction is necessary, but too much friction is also not good. I mean, too much friction, you'll not be able to move forward. Zero friction, you'll be slipping. I mean, how do you walk forward? Unless there is a little bit of friction on the ground, you'll not be able to walk forward. Try walking on ice or something, smooth ice, or on an oily surface, or on, it's occasionally risky if you go into the bathroom and there's a layer of film, a film of soap lying on the bathroom floor. There's a risk of slipping. So little friction is necessary. Too much friction is not very good. So for bicycle racing tracks, the tracks are designed to offer little friction so that you get this forward motion. Otherwise, the bicycle tires will keep slipping instead of moving forward. But that friction effect is not a huge effect. So that's why you can afford to ignore it. Anyway, our problem is to account for motion through air, horizontal motion through air. Now we will look at a third kind of motion through air. First is, we talked about vertical drop through air, as in a parachute is dropping. Second is horizontal motion through air, as in a bicycle rider moving forward horizontally. The third is projectile motion, which has both a vertical component and a horizontal component, as we are about to begin this discussion. Let us see. This is something that you would have read at school, so we shall initially recall the school knowledge of projectile motion. And the practical application is trajectory of an artillery shell. Let us see. Projectile motion has two components, one along the x-axis, horizontal motion, and the other along the y-axis, vertical motion. I hope you know what a projectile motion is like. I mean, an artillery shell is fired at an incline. If you have seen these news items on war going on right now in Ukraine, or even in the Kashmir border, I mean, border in Kashmir, the line of control with Pakistan, you will see artillery shells being fired. The barrel of the artillery cannon is kept at an incline. The shells that are being fired out of the artillery cannon have two components of motion. One is a vertical motion and along the y-axis, and the other is a horizontal motion along the x-axis. So the projectile motion has two components, one along the x-axis, horizontal motion, and the other along the y-axis, vertical motion. So the equations of motion are, let's not for the time being worry about air drag. Basic simple thing, just like in the first bicycle rider problem, initially we did not account for air drag. Uh, Incidentally, if you did not account for air drag in this parachute is dropping problem, you'll just have gravity, nothing else, right? So this will just keep growing, growing, and growing. V will keep growing. So if you integrate this equation without air drag, dv dt will be equal to a constant g. So V will be equal to gt, right? So you'll just keep growing to linearly large values, but air drag offers a resistance. So early linear growth will saturate. This part is because of the air drag. So initially we shall look at motion, the projectile motion without air drag. Let us see. So the equations of motion, there are two accelerations, one along the horizontal direction without air drag, and the other along the vertical direction. So when you do not have air drag, along the after the shell has been fired, or you can even think of catapult. You would have played with a catapult probably as in your childhood. So if you use a catapult, so you throw it at an incline, shoot the catapult at an incline. After the projectile has been released, along the horizontal axis, it does not feel any acceleration, but along the vertical axis, it feels a downward acceleration due to gravity. Okay, so this is the diagram of a projectile motion. This is the y-axis, this is the x-axis. The projectile has been projected at an angle alpha. Okay, so the projectile has an initial velocity of v naught. V naught is in this direction. This is your barrel of your Bofors cannon from which artillery shells are being fired, right? So projectile has an initial velocity of v naught directed this way with a projection angle of alpha. Now along the horizontal direction, d2x dt squared is equal to 0 if you have this equation. Therefore, dx dt will be a constant. d2x dt squared is equal to 0. dx dt is a constant which we are calling v subscript x, velocity along the x direction. dx dt is velocity along the x direction, and it's constant velocity. And along the vertical direction, dy dt is equal to vy. This will not be a constant, as we shall see, because this is not a constant. d2y dt squared is equal to minus g. We'll come to that later. dy dt is the vertical velocity. So initial value of Vx at t equal to 0 is V naught cos alpha. Why? This is being projected at an angle alpha. So the horizontal component will be V naught cos alpha, and the vertical component will be V naught sin alpha. So initial value of V naught x subscript x at t is equal to 0 is V naught cos alpha, and it will stay the same all the time. Why will it stay all the same all the time? Because along the horizontal axis, Vx is constant. Now, initial value of Vy at t equal to 0 is V naught sin alpha. Okay, since Vx is constant, dVx dt is equal to 0. If dVx dt is equal to 0, acceleration along the, so d2x dt squared is equal to 0 and dx dt is equal to vx. So if you put the two things together, you will be able to write dvx dt is equal to 0. So you can immediately solve this equation, d2x dt squared, you can solve it. The xt integral will be, so this is d2x dt squared is equal to 0. This is dx dt is equal to vx is a constant, and therefore x is equal to vx into t plus a1, where a1 is an integral constant, integration constant of integration. So when t is equal to 0, x is equal to 0. At t equal to 0, you are at the origin of coordinates here. So when t is equal to 0, x is equal to 0 at the origin of coordinates. So x is equal to 0 into this thing into 0 will be 0 plus a1. So a1 will be equal to 0. So x is equal to vx into t. And what is vx? V subscript x, it is v naught cos alpha into t. So vx is equal to a constant quantity. What about dy dt? dy dt is vy. And d2y dt squared is equal to dvy dt is equal to minus g, right? dy dt is equal to vy, so therefore d dt of dy dt will be dvy dt, and that's equal to minus g. So dvy dt is equal to minus g. We will integrate this equation. We will get v subscript y is equal to minus gt plus a2. A2 is the second integration constant. Now, when t is equal to 0, vy is v naught sine alpha, the initial vertical value of the vertical component of the velocity. So that is the condition we are putting. T is equal to 0, vy is equal to v naught sine alpha. Therefore, A2 is equal to v naught sine alpha. Okay, so Vy will be equal to, just give me a minute and I'll finish this discussion and then we'll stop for the day. Minus Gt plus is equal to v naught sine alpha. So, but Vy is dy dt, right? So, dy dt is equal to Vy. Dy dt is equal to v naught sine alpha minus Gt. So, when you integrate this thing, y is equal to v naught sine alpha t, this is constant, v naught sine alpha t minus gt squared by 2 plus a3. When t is equal to 0, y is equal to 0. Once again, at t equal to 0, you are at the origin of coordinates, so y is equal to 0. At t is equal to 0, y is equal to 0. Therefore, a3 will also be equal to 0. So y is equal to v naught sine alpha into t minus gt squared. So what we have here is a set of parametric equations whereby x is a linear function of t, as you can see here, and y is a parabolic quadratic function of t and t squared. So hence we have a set of parametric equations in the form of x as a function of t and y as a function of t. Okay, so I shall stop here. On Friday, we shall continue with this discussion. So up to whatever we discuss till Friday, I will keep as your examination syllabus, right? That is my plan. So if you have any questions to ask, you may ask me. Anyway, I'm stopping the recording. If you don't have anything to ask, you may please
Sir,
leave. Yes, sir.
sir, from next Monday, our exam